always been like a physics class.
Well, good morning, everybody. Congratulations, you got here on the second day. You survived the parking lot, right? I don't want to spend too much time on this, so maybe just a couple minutes. Is there anything I can answer right now? If you've been in the syllabus, you've been looking at Canvas, is there anything? Yeah.
So for Wiley Plus,
yes.
You just get the free trial first, and then use once it expires, then use the codes or
whatever. And we'll talk a lot more about that tomorrow. Yeah, but yeah, you want to get into Wiley Plus and like enable the free, right? Because you need to be in the book, you need to be looking at the first homework assignment, all that kind of stuff, right? I know those of you are on the wait list. I can't add you till tomorrow, right? But you'll have access after that, and the homework like is due this Saturday. However, if you've had a science class like in high school or here, like a chemistry class or biology class, you can probably do the chapter 1 homework. It's unit conversions and some trigonometry, I think, right? So hopefully that's, I often think that the real physics starts in chapter 2. Any other things you read or saw worrying you have to know, figured out right now? Tomorrow's a big day because we're going over a lot of the details, okay, about how the course works and things like that. So don't miss tomorrow if you can possibly help me. If you're going to miss tomorrow, you got to email me, right? Because we got to figure out how to get you the information. All right. So we did that. Let's talk some science and some physics and some stuff today. You're going to notice that I'm not going to take roll today. Right? Again, I'm going to do all of the add drops and everything tomorrow. So don't panic because I'm not taking roll. But my goal here is to do all of chapter 1. Hopefully a lot of this is review. And then get straight into chapter 2 because we need some time on chapter 2. So, what is this? It's a meter stick. Okay? And how do I know it's a meter stick? Well, it's a meter long, right? It's not 36 inches long. It's 39.25 inches long, right? Okay, so this is a meter stick, and there's many different unit systems in existence. However, I boil it down to 2. There is the perfect unit system, and then there's the dumb unit system. All right. So, what makes the metric system so good? Well, okay, every unit system is pretty accurate. Precise. And precise. We can argue what those terms mean later. I wonder where they came up with the idea of having everything divisible by 10. What do I mean by that, right? How many centimeters are there in 2.67 meters? 267. Oh, you did that kind of fast. How did you do that so fast? Well, the centimeter's 100, and I moved the decimal point over and done, right? So 2.67 meters becomes 267 centimeters. Okay. How many inches are there in 7.69 feet? Ha! Can't do that one so fast because multiplying by 12 isn't something we really practice, right? So the metric system's got that going for it. Let me share with you a piece of information that maybe you didn't realize. So, how many countries use the metric system? A lot. How many countries don't use the metric system and use the imperial system of units? Okay? The answer is 3. Okay? Right? And we're the big gray thing over on the side, right? Okay? So, yeah. Here's another secret. Here in the United States, we actually use the metric system. An inch is defined as 2.54 centimeters. our weights, our lengths, our volumes, everything, our quarts, our ounces, our whatevers, right? That's all defined by its metric equivalent. So we are, in fact, using the metric system everywhere we go. We just put some 12 inches in a foot. Why? What's you guys know? Do you guys know the original definition of the yard? It was like the distance from the king's nose to their outstretched left hand or something like that, right? Basing a unit system on a person is not a good idea, right? Especially royalty, because then they inbreed and weird things happen, right? And it's just, it's a disaster, right? So the metric system defines itself according to physical constants in the universe, most of them having to do with the speed of light. And I don't want to get into metrology because it's just going to bore you and all that kind of stuff, but you just need to know that the metric system is invariant, meaning it doesn't change over distance and time and all that kind of stuff, whereas any other unit system kind of does weird stuff, okay? Why are we talking about unit systems? Well, units are really, really important, and we need to know, because we live in the United States, and because we have this sort of different unit system that everybody else in the world uses, and by the way, if you're going into any kind of medical field, you're going to be using the metric system all the time. If you're going into chemistry, you're going to be using the metric system all the time. If you're going into engineering, they're dumb, okay? Because for some reason, engineers in the United States always use the imperial system. So this is why we're going to spend some time on it. I mostly use the metric system in here. But how do you, give me a 3-digit number. 3.47. I heard 347, but we're going to do 3.47. Okay. We have 3.47 meters or feet? Feet. Okay? And we want to find out what 3.47 meters is. What's the equivalent in feet, right? Okay? So how do we do that? Hey Siri, what is 3.47 feet in meters? So I turned off her voice. But she says 1.06. But that's how you do it, right? You just ask Google. But what is Google or Siri or anything else doing?
Rounding.
Well, okay, they round, but what do you need to get from this to meters?
You know how many feet are in a meter?
Yeah, we need what's called a conversion factor. You're hitting it, right? Okay? So we can go look up the conversion factors. And you're like, well, Mr. Baylor, the computer can do it. You're not always going to have, well, actually, you're going to always have the computer with you. Never mind. 1 foot is equal to 0.3048 meters. Or, and this is the kicker, okay? 1 meter is equal to 3.281 feet. Which one do I use?
You times with 1 and divide by 1.
That's the correct answer, but how do you know which one? The answer is, there's only one way to do it. You always multiply. Now this is a trick, okay? But you're always going to multiply. What do I mean by that? You're going to multiply by a ratio. You guys know that multiplication and division are really not different from each other, right? Division is just multiplying by the inverse. Okay, so that's kind of where I'm going here. So if I have 3.47, I want to know how many meters that is. I start with really bad handwriting is what I do. Where's my 3.47 feet, and then I'm going to multiply, and I make a big ratio here, okay? And with this ratio, I'm going to let the units do the talking for me. In other words, I want to get rid of feet. So where would I put feet? Numerator or denominator to get rid of it? Goes in the denominator, right? So it's upstairs right there. I want it downstairs over here, which means that meters is going to go on top. And now, which of those conversion factors do I use? The answer is it doesn't matter. The answer is you can use either. And we're going to do both. So let me do 3.4. Man, my 4s are having trouble today. 3.47 feet. We'll do another conversion factor over here. Feet goes in the bottom. Meters goes on the top. So I could use the 1 foot equals 0.3048 meters. Where do I put the 0.3048 meters? Top or bottom? Top. The meters is in the top. The number that's near the meters goes with it. So that means I put the 1 foot on the bottom. Okay, in the other example, where do I put the 3.281? On the bottom. Why? Because it's 3.281 feet, right, for every meter. Okay, everybody pay attention. This is a line right here in the middle of class. Everybody on this side, do the top one. Get your calculators out. Everybody on this side, do the bottom one. Let's see what we get. Okay, this side of the room, anybody got a number? Shout it out. 1.057. Does somebody else get 1.057? Yeah? Good? All right. 1.057 meters. Okay. This side of the room, what'd you get? 1.057, right? A little bit of round off error maybe. Because numbers are numbers, right? But the point is that you're always just going to multiply, right? Multiply by a ratio and make sure that you get the units upstairs or downstairs in their right spots, and the conversion factor goes along with it. This is how we teach the machines to do it for us. And it's important to know where it comes from. Okay, so what do we do if, let's do this. What do we do? Okay, how do we find out how many seconds there are in 1 year? I mean, we can ask Google, right? But let's do it by hand. Where do we start? What do we know?
Seconds to minutes.
Yes, but what do we know? We know it's 1 year, right? We're given that it's 1 year. So that's where we're going to start. Okay? So 1 year. And now I'm going to multiply, right? And what am I going to put in the bottom? A year. And now I got to get to something, a conversion factor that I might know. Into days, maybe? Right? I can't go straight to seconds. I can't do that number, right? But maybe I could go to days. Okay? So in 1 year, how many days is that? 365 and a quarter. Okay, because leap year stuff, right? Okay, now that I'm at days, notice I can just keep multiplying here, right? Where did days go? Top or bottom? Goes in bottom. Okay, maybe we can go to hours, right? Okay, because we know that in 1 day there's 24 hours. All right. What goes on the bottom? Hours. Because, again, what I'm going for here is the ability to have these things divide out from each other, right? Okay. And the year disappears and so on and so forth. Okay. In 1 hour there are, okay, well, I'm going to shortcut 30. Yeah. Where'd my undo button go? 3,600 seconds. So I was getting tired of writing stuff here, right? Okay. It's 60 minutes in an hour, and then 60 seconds in a minute. And what's 60 times 60? 3,600. Okay, right? So anyway, you don't have to shortcut it like that. But then in my calculator, right, I'm going to take 365.25, multiply it by 24, multiply it by 3,000. I don't care what the answer is. I just want to know, right? But my point here is that when you're converting units, multiply, right? And be clever about top and bottom where the different units go so that you can eliminate them, right? And I'm left, what am I left with in unit-wise? That's seconds right there, right? And that's what I wanted. All right. Let's see. Yeah, okay, it's time for a quiz. So, what we're going to do for the next 15 minutes is I'm going to teach you how quizzes work in this class, right? This quiz is more about learning how to do quizzes than it is about, I mean, the quiz question is kind of important. It involves unit conversion, surprise, surprise. Let's see here. What I want you to do is everybody take 3 of these sheets. We're going to run out, and some are going to have more, so in the back, just sort of send them sideways, whatever way you need to go for people. Everybody gets 3 of these sheets. And if you get extra sheets in, you can have them. Okay, we've got quick sheets. Yeah, there should be, those of you that got extras, you can have send them this way. Oh, yeah. There's more seats in that. Yeah, but people are limited. All right, everybody got 3? All right. This isn't working. 1 second. I had to redo my tech this time with the recording stuff, so it doesn't always work the way it's supposed to. There we go. All right. So, don't forget to put your name on it. Okay? I always make fun of Dr. Staff. Staff teaches a lot of classes on campus, doesn't he? Or she? Right? It says no idea what the teacher is. Okay, so quizzes in here are not about points. They are really about you teaching each other. And so to that end, quizzes almost always are going to come in pairs. In other words, there's going to be, like for today, quiz 1.1, chapter 1, first quiz, okay? And a quiz 1.2. They're going to have the same point value, right? So quiz 1.1, I don't remember what I said. 3 points, 2 points? 2 points each, okay? So it's 1.1, 2 points, right? Quiz 1.2 is also going to be 2 points. All right, got to put that on the board so I remember. So what you're going to do, okay, is you're going to just, in the first box, 1.1 out of 2, and in the second box, 1.2 out of 2. I'll always sort of just say, okay, this is the quiz numbers, and the points are, the same between them, okay? And believe it or not, the question for 1.1 and the question for 1.2 is going to be exactly the same question. So why are you using 2 boxes? I want you, for the first quiz, to try it all by yourself. I want you to try it all by yourself because you need to find out where you're having trouble, whether or not you're getting this kind of thing. And if you've ever been in a class where you've been listening, and you go, oh, wait, and the teacher asks a question, you're like, oh, wait, I know the answer, oh, and then the person right next to you blurts out the answer. What happens to your, train of thought when that happens? Yeah, it derails, right? And what you've been robbed of is a chance for your neurons to link that pathway through and connect pieces of information, right? And so what I want to give you is 30 seconds, 2 minutes. It depends on the quiz question how long I give you. But I want you to try it first on your own, right? Find out where you're at. And then you are going to write down the answer in the box with hopefully some sort of explanation. Now, a lot of the quizzes will be like multiple choice, so you can just say I choose A, or just write A, and then give me a reason, right? This is a terrible reason, okay? Just because I say something doesn't necessarily, right? There should be some argument, mathematical, physics, whatever, okay? Side note, you are going to keep these for the entire semester. You're going to turn them in at the end of the semester, okay? So if you want a permanent record of everything that's going on, work the quizzes in your notes, right? And then you can put the cliff notes on here, right? Your answer and a really short explanation, okay? But I will take these at the end of the semester and you won't see them again, okay? So just so you are aware of that, right? Or do it all in the quiz sheets, take pictures, insert it into your iPad notes, whatever it is you want to do. But do know that these will disappear at the end of the semester. Okay. And so you're sitting there, you've done it, you've answered it, right? What's the second box for? What I'm going to do is I'll call time, and then I want you to turn to each other and tell each other what your answer is, but most importantly, why. Why did you pick the one that you picked, right? And you can be honest. You turn and say, I guess, right? And so you're going to start a back and forth. And what you're doing there is teaching each other. And you're going to find out what you know and what you don't know. So the second box, if you change your answer, right? If somebody teaches you something and you realize you missed something or whatever, right? You are going to write down the new answer and the new reason, or maybe why you changed, right? I forgot to consider the blah, 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 right? Okay? This is made up. There's a website for making stuff. But you're going to, if you change your answer, you're going to write it there. If you keep your answer the same, just draw an arrow. Don't rewrite everything. An arrow just connecting the boxes will tell me I'm keeping my answer the same, right? Or just say I'm keeping my answer, whatever, right? Just indicate that you're not changing your answer. This I called the group quiz. You do not need to answer the same as the group. This is still your individual answer. It's just an answer that has come about because you had reflection and teaching and an opportunity to communicate. And then we'll fight over what the real answer is, and then you score it. You grade yourself. Often the hardest grader in the room, okay? And you're like, sweet, I just got 50 points, right? 50 out of 2, okay? Right? I mean, the points actually don't matter because I give out about 150 points worth of quizzes during the semester. You only need 50 to get an A. There's no extra credit. As soon as you get to 50, it just truncates, okay? So what usually happens is people are all like wigged out about the numbers for the first 3 weeks. And then after that, you get to the halfway point of the semester, you're like, I've got 50 points. And by then, you're like, oh, quizzes aren't really about points. They're about this opportunity to teach each other. So, with all that being said, let's go through the first quiz, right? All right, okay? So here is your quiz question. I'm going to put it up on the screen, okay? And then you're going to figure it out on your own. I'm going to give you like 90 seconds, okay? I want you to tell me how many cubic centimeters there are in 1 cubic meter. There are 100 centimeters in 1 meter. There's the conversion factor for you, okay? But I just want you to tell me how many cubic centimeters there are in 1 cubic meter. About 30 more seconds. Okay, at this point, hopefully you have something written down in that quiz 1.1 box. It could be just the answer. You could have done the work in your notes or something like that, right? Because I know there's not a lot of room in that box. But you want to have something written down. And we're not going to change this answer now, right? This one's going to be set in stone. Any changes you make are going to go where? Second box, right? The 1.2 box. So right now, turn to each other, tell them what answer you got and why. Go! I'm sorry, yeah. We need 3. Okay, at this point, write down any different answer you may have. Give a reason maybe for why you changed it. If you didn't change it, what are you going to do? Arrow down. Normally, I won't tell you or remind you to write down your answer. Hopefully, as you're discussing things, right, you'll make the changes, or maybe you'll just both agree and then you just draw an arrow, right? Okay. But because I'm walking you through this, I'll give you time right now. Just in 1.2, if it's different answer, and then why. If it's the same, draw an arrow. Okay. So let's figure out what the answer is, and we're going to. Everybody knows that you figure out stuff by voting, right? And so to maintain the illusion of democracy, I'll let you vote on the answer. All right. So how many of you say the answer is 1? 1 cubic centimeter per cubic meter? No? Okay. How many of you say it's 10? How many of you say it's 100? Okay. A few of you. Okay. 1,000? Is anybody sensing a theme? 10,000? 100. Why am I always going by tens? Right? Where was I? 100,000? A million? Ooh. Anything more than a million? Okay, so we saw 2 peaks in the voting populace, okay? One was at 100 and the other was at 1 million. The 1 million camp was in the majority, so we'll make them defend their position first. Those of you that said 1 million, what's your argument? What are you thinking? How'd you get to your answer?
So if there is 100 centimeters and 1 meter, we could just basically cube both of them. We can cube in order to get our units into cube, and then we would apply the cube also to the number.
Oh, wait. So if I cube this side, I've got to cube everything?
Yes.
And so that would make this a centimeter cubed, right?
Yeah.
But what's 100 cubed?
1 million.
It's 1 million. Okay. Anybody do it any different way? Yeah.
I thought about like the 1 meter cube.
Okay, so you kind of visualize.
Yeah.
I apologize for my lack of artistic ability here. Okay, right? And you're like, well,
100 centimeters.
100 on that side.
Yeah.
100 on that, 100, right?
Yeah.
And to find the volume of something, I go, what's it? And 100 times 100 times 100 is a million. Okay.
This is a test of the State Center Community College first to note notification system. This is only a test. Attention, Brooklyn City College. This is a test.
Yeah, you don't need to repeat yourself.
Community College first
Thank you for interrupting my lecture.
This is only a test.
We were learning something. Thank you. All right. So visualization, mathematical, okay? The way that I taught you to do units and multiplying stuff together, right? So we have 1 cubic meter, right? We start with 1 cubic meter, right? And then I multiply, right? And what do I put on the bottom? Meters. What do I put on top? Centimeters. What do I put on the bottom? 1. And up here I put 100, right? Okay. Now, can I just cancel both of those? No, right? That would only bring it down to squared, wouldn't it? Okay. So if I'm starting with a cubic meter, I've got to do another one of these. People that answered 1 million, am I getting your kind of thought process here? Okay. Those of you that answered 100, where'd you go wrong?
I see a cube root on both sides.
Yeah, cube root? Dude, you're going for the hard stuff. You probably didn't realize that, like, the conversion factor is without the cubes, right? And you can't just cube the centimeter and the meter. You got to cube everything. Or you got to do the conversion factor 3 times. So you might be sitting there going, oh my gosh, I just totally screwed up. I can't do. No. What do we do with mistakes? We learn from them, right? So you want to write down in your notes. Okay, I messed this quiz up. I got to make sure to remember to check my units, right? Make sure that you don't make assumptions about conversion factors or whatever kind of mistake you made there. Learn from it. It's awesome. You're actually in a better spot than people that got it right. Because you learned something. People that got it right are like, yeah, I got it right. Okay. So all right. So now, score yourself, right? If you answered, say, 100 the first time and 1,000,000 the second time, 0. And then 2 on the second one. Maybe you need some pity points today because you've had a rough day. 1 out of 2, right? Like, you're scoring yourself, right? The points actually don't make any, okay? You put points on things because otherwise students will ignore it. Doesn't have points, right? But the idea here, the chief idea of any quiz is really to give you a chance to see where you're at and then give you a chance to teach each other. And that's what I'm talking about, like you interacting with each other. Generally, we'll do 1 to 3 of these per lecture. It really depends on the topic and what's going on, how many questions we have, and blah, 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 right? So you can anticipate that. Bring your quiz sheets all the time. I know, they're annoying because they're actual paper, but you'll get over it. All right, let's see. We did all that. I should probably talk about this. So, just real quick, this is something you're going to come across in reading. You're going to see it on YouTube's. You're going to see, I'll talk about it every once in a while. In physics, we actually often don't care about what the actual answer is. Okay? What we're more concerned about sometimes is, like, are we in the ballpark? Does the answer make sense? And how do I know if it makes sense? We do something called an order of magnitude calculation. And the way I like to talk about this one is, give an example. So let's say that we invite an engineering major, a physics major, and an English major to measure the volume of this room. Okay. So 3 students, 3 majors, they got to measure the volume of the room. What does the English major do? Cries, right? They just cry, okay? Because now we're measuring something and it's not in their bailiwick. Okay, what does the engineering student do? I want the volume of air in this room. What do you do? Oh, okay, so you get a measurement tool. Maybe this one, okay, right? And how are we going to find the volume? We got to measure the length, and then we got to measure the right. And so engineering student takes thing. I need a laser. Right? Don't, I need a laser. Right? And then, oh, wait a second. The room's not a cube. So now I need an angle. Man, there's heads in the room. I gotta subtract the volume of everything. There's people in the room. Oh, I know. We'll fill the room with water. We'll fill the room with water and then we'll measure the volume. Why are engineers like that? Why are they like so precise and stressed? Because you can get sued. Right? You do it, Boeing. Right? Okay? You do it wrong, right? People's lives are on the line. Engineers is where the rubber meets the road, where science goes into the public space, right? And so it's important that you get things right, which is why I have an emphasis in this class of, yeah, let's get the right answer. That's really when you got that 100%, right? Okay? Now, the physics major waltz into the room, probably very arrogant. You know, physics is the chief science of all science. Okay, let's see here. It's about 10 meters, 3 meters, 300 cubic meters. When's lunch? What's the difference in approach between the engineer and the physicist? It's like a precision, right? The engineer wanted to know exactly. The physicist wanted to know within an order of magnitude. And that word, order of magnitude, means power of 10. So a physicist would be fine with knowing that this is on the order of hundreds of cubic meters. It's not thousands, it's not tens, it's 300-ish, right? So if I asked you, how many blades of grass are there in 1 acre of grassland? You need to start making some assumptions. What kind of grass? Is it prairie grass? Or is it like that putting green grass where all the blades are like really close together, right? You might take a measurement of, say, maybe 1 square foot in that prairie grass and count the number of blades, right? Now, is every square foot always going to have 131 blades of grass? No. But you can get an idea for how many blades of grass there are in an acre by taking a sample. It's an order of magnitude. It's not going to be exactly the number of blades of grass, right? But it's going to be close. How many piano tuners are there in New York? How many hamburgers can you get out of a cow? These kinds of questions vary depending on how big's the cow, how many, right? What cuts of meat, right? But you can get an order of magnitude. You can be within a power of 10 of what the actual answer is. And oftentimes, that's really all you need to know. So if you see an order of magnitude calculation or somebody mentioning that, oh, this answer is within an order of magnitude, that's what we're talking about. We're saying it's in that range where we say, yeah, our assumptions are holding. So I just wanted to pass that by you, right? Make sure that you understood when I drop that language. All right. Let's do chapter 2. Let's get started. That was chapter 1, okay? So ideally, between the book and me, you now are able to do the questions in chapter 1, okay? I might have lied. I think the trick might come in chapter 3. All right. Let's, okay, so chapter 2 is where physics really starts to happen, okay? It's, we're really going to start defining how things move, and we use a series of symbols, ideas. Symbols represent ideas, right? We use these series of symbols in order to talk about how something is moving. So I want to talk average versus instantaneous, but let's back up because you probably haven't read chapter 2 yet. Some of you haven't even clicked on the book yet. So I'll be nice and just sort of give you some information. This would be the kind of thing I'd almost expect you to have read already and have these definitions down, right? So that I can talk about how to use them. That's where we want to spend most of our time. But we'll back up. Okay, so describing where something is. How do we describe where something is in the universe? Right? But in a more scientific sense, we've got to be able to compare positions of things, all kind of stuff. So what, like in math, what did you do to find a point in space? Yeah, there had to be some sort of reference, a coordinate system of some kind, right? Well, let me tell you about a superpower that you now have because you are in this class. You have the superpower of deciding where the center of the universe is. You always knew it was you, right? No. Okay? What I'm talking about is you get to pick where 0 is. You got to start somewhere. We want to reference everything. So, here. I hate me when I do this. Okay. All right? So I marked my 0 point. Okay? This is 0. What's that way? Positive or negative? Positive. What's that way? What's that way? Positive up. Negative, right? We got sort of the standard Cartesian coordinate system going on here, right? Okay. So now, if I go 1 meter this way, what would you say my position is?
1 meter positive.
Positive 1 meter. I want you to get used to start thinking. I know mathematicians told you, well, there's no plus, it's inherent, it's implied. No, I didn't. Positive 1. Okay? All right. So if I'm here at 0 and I go this way 1 meter, now what is it? Negative 1. Okay. All right. So now, if I walk 2 meters this way, and then I walk 1, 2, 3 meters this way, how far did I go? I went 1, 2, 1, 2, 3. That's 5 meters, right? The distance I traveled was 5 meters. But my displacement, my reference from where I started is what? Negative 1. Is there a difference between distance traveled and the displacement of an object? Yes. Now, can they be the same? If I start here and I go negative 1, how far did I go? 1 meter. I didn't go negative. I traveled 1 meter, right? But my displacement is what? Negative 1. If I start here and I go 2 meters, and I stop, how far did I go? 2 meters. What's my displacement? Positive 2. So they can be the same, but they don't have to be the same, right? Displacement and distance traveled. 2 different things. 2 different ideas. How do we represent symbolically? How do we represent the location of where something is? What symbol do we use? Hint, Cartesian coordinate systems. X. Right? X marks the spot. Okay? So, okay. Do not, okay, just stop for a second. I'm about to put some math on the screen. Okay? Symbolic math, not numbers. Symbolic math. You've been trained, your brain has been trained into a pain response whenever math appears on the screen. Okay? Your brain is going to want to shut off and just start writing things in the hopes that somehow it gets seared in there at some point. Right? Okay? Don't do that. Okay? Math is bad. But in this class, it's a foreign language. We use it to express ideas, okay? So please don't turn your brain off just because I'm going to go in and write down X, right? Okay? Let me introduce you to another symbol, okay? And this is the one we're going to use to indicate that there's a difference between where we are versus our displacement, right? The displacement being a comparison between where we end and where we started. That symbol is a delta. It's just a big triangle. Okay, it's the Greek letter delta. And it literally means take the final position and subtract off the initial position in the case of a delta x. Okay? All right. So I can indicate position just with x. I can indicate displacement by saying this delta, this difference between where I start and where I end up. So like if I'm here at 0 and I end up at -1, what's my final position? -1, right? Okay. What's my initial position? Where did I start? 0. What's -1 minus 0? -1. Right? Okay. It works. How do I now figure out how fast I did it? What's it called if we change our position in time? That's velocity. If we change our position in time, what does delta t mean? Change in time. The 0 time is always just 0, right? T0, okay? But I could start here and do the tortoise. 5 seconds to go 2 meters, right? Okay. My displacement is what? 2. My time is 5, right? 2/5, right? Unit-wise, what's the top unit? Meters. What's the bottom unit? Second. So a meter per second would be my unit for that velocity, right? Or I could do the 2 meters in 1 second. Which one was faster? Second one, right? Because I went 2 meters in 1 second, and 2 is bigger than 2/5, right? Okay? So a velocity is trying to indicate how fast something is moving. What symbol are we going to use? V? Wouldn't that be convenient? Oh, well, it turns out that that's exactly what we're going to. Okay. Right? We'll use the symbol V. Okay? And physicists usually write that V as a kind of a curly script. Got some wiggles on it. You can write the V however you want. All right, so we got that idea. Okay, then there's one more idea that we use to try and capture how something moves. So we got position, we got velocity. What's the last one? Acceleration. This is where everybody loses it. Okay? What is acceleration? I can do it symbolically. Okay? It's going to be a change in velocity in time. Okay? By the way, my velocity has units of meters per second. Right? So, okay, so let's see. It's a change in velocity, a change in time, which means the units are going to be what? What are the units of velocity? It's a meter per second, and then I'm dividing by a second. So it's a meter per second, which is difficult. You don't want to say that all the time. Okay? Mathematically, when you have a fraction divided by another fraction, you put it together, right? So it becomes meters per second squared, and that's often what we say when we're talking about an acceleration. Okay, so we've got down sort of what these definitions are, mathematically, symbolically, what they are. But what is an acceleration? Like conceptually?
How fast is the object changing?
No, that's velocity.
A change in velocity.
It's a change in velocity. If velocity is how fast you're going, acceleration is how much your motion is changing. So if I start here, and I walk with exactly the same velocity all the way across the room, what's my acceleration? It was 0. It was a constant, but the constant was 0. What does 0 acceleration mean? No change in motion. Velocity. Velocity is motion. I didn't change my motion. Okay? But now if I come over here, and I start over here, and I start slowly, and I get faster and faster and faster and faster, did my motion change? Yes. Okay, that was changing motion. My acceleration was positive or negative? How'd you know? Okay, all right. Starting here. Starting fast and then slowing down. Did it? What direction was my displacement? Positive or negative? Positive. We all agreed that I moved in the positive direction? Okay. What direction was my velocity? Which way was I moving? I was moving in the positive direction. What direction was my acceleration? My acceleration was negative. I was moving positive, but slowing down, which means my motion was changing in the opposite direction to my motion. Are directions important?
Yes.
Absolutely. In chapter 3, we're going to talk a lot about directions, okay, with this thing called a vector. But for now, we're going to base this and make sure that we're all on the same page, right? If I start here at 0 and I speed up, what direction is my motion, my velocity? Positive. What direction is my acceleration, my change in motion? Also positive. I sped up and in the same direction I'm going, okay? So now, okay, I am going to be, my velocity will be which way? Negative, okay? And I am going to start fast and slow down, right? So I'm going to start at a sprint and then slow down. What direction was my velocity?
Negative.
What direction was my acceleration?
Positive.
How many times are you going to make this mistake? All the time. Okay? You're going to start by making it all the time, and you're going to figure out where your assumptions are wrong and correct. And you're going to try and get all those mistakes out of your system. Question?
Okay, so a change in negative velocity, positive acceleration.
Yes! Okay, everybody hear that? Wait, a change in negative velocity. All right. I'm going fast and I'm slowing down. What direction was I going? Negative. But my change, the way my velocity changed, was pointed that way. I was slowing down, right? If I'm going one way and slowing down, my acceleration has to be against it, right? If I throw a ball in the air, okay, after it leaves my hand, what direction is its acceleration?
Acceleration negative is going down.
An entire education, K through 12, and we're still confused about it. I don't blame you. I blame your teachers, okay? What direction is the acceleration for a ball that's in the air? What direction does gravity point? Ah! Right? If the ball's going up, is gravity pointing up? No! Right? The acceleration, even if the ball is going up, is pointed which way? How do you know? It's slowing down. Right? It leaves my hand and slows down and then gets to its maximum point, right? Which way is it moving? Up! And it's slowing down, so which way is the acceleration? Gotta be down. And then it gets to here, right? And then it starts coming down again, right? What direction is it now going? Down. Its velocity is down, right? And it's speeding up. Which way is the acceleration? Down!
What?
Gravity never changes its direction.
The acceleration increases.
No!
No?
The acceleration stays the same. It points down at 9.8 meters per second squared. We'll get into that in chapter 4. Okay? The point I'm trying to make is, okay, where are we messing up? Where are we messing up?
Yeah, gravity.
Yeah, I thought I understood gravity before I came into this room. Let me tell you what's happening. Okay? This is what's happening in your brain. Most classes you walk into, okay, you come in with your knowledge bucket, okay, and it's empty. when you go into history class, you go into philosophy class, you go to political science, whatever, right? You come in and you go, fill my bucket. Okay? And the teacher just goes, right? In physics, you're coming in with your bucket, and it's got however many years old you are of information, of knowledge, of things that you think you know. And there's some dirty water in there. Okay? There's some really dirty water in there. For example, why is the sky blue?
Because of light and sun rays interact with the atmosphere. I'm trying to hear that right now.
Yeah, you're actually right. It's the first time I've heard the right answer. Why do most people think the sky is blue? Because the ocean is blue. What color is water? It's transparent!
Clear.
What color is the ocean on a cloudy day? Not blue, it's gray. Right? The ocean is blue because the sky is blue. The reason that the sky is blue is because something called Rayleigh scatter. But you know what it is. But nobody else knows it. Right? That's bad information. Okay? So what do I have to do in here? I have to dump your buckets out. I do. And sometimes it's rough. You're experiencing it right now, right? You're like, -1, right? Yeah, right? Slam it down, go become an English major, right? No, right? I have to correct misconceptions that you are just, you're at a stoplight, okay? Light turns green. You hit the gas. In the instant you hit the gas, how fast are you going? 0. What's your acceleration?
1. Oh.
Not 0. It can't be 0 because in the next instant, what will you be doing? Moving. You are changing your motions. So, what direction is the force on you when you hit the gas and start accelerating forward?
You restate that?
Which way are you pushed when you accelerate? Push back into the chair?
Yeah.
Right? You hit the gas. Wrong. There's only one direction you can be pushed if you are changing your motion in the forward direction. The push is forwards. Name the object that's pushing you backwards in your chair. That's not an object.
Is it the air?
No. The car is pushing you which way? Forwards. Do you see what's wrong? You don't understand the physics. That's fine. We're going to get to that in chapter 5. Okay? The point I'm trying to make is that you think you know what acceleration is. You probably think acceleration and velocity are basically the same thing and I don't have to worry about it. Do you need to worry about it? Yes! My teacher's shouting! There has to be something here. And so, together, we are trying to throw out the dirty water and replace it with clean water. That often comes in the form of, golly, you are really wrong. Let's figure out why. It is excellent to be wrong in here. Like, it really is good, because that means we're identifying dirty water. The hard part is getting that dirty water replaced with clean water, okay? Quizzes, the things we talk about together, all of that is designed to get you really thinking about what's going on. Okay, so back to this whole acceleration thing, right? And we'll just do the ball again, okay? When the ball is moving upward, do you agree that the velocity changes direction? Does the velocity go up and then down?
Yeah.
We're good there? Everybody usually has a perfect concept of what that is, okay? Now, was the ball speeding up or slowing down in the first half of its flight? It was slowing down. So if it's moving up, positive, but slowing down, what direction is its acceleration? Down, negative, right? And then at the top, it turns around, stops, right? Goes from positive velocity to negative velocity. So now it has negative velocity, but is it speeding up or slowing down? It's speeding up. So if it's moving down negative and it's speeding up, what direction is it the acceleration? It's also negative. Because it's getting faster, right? So something's changing its motion and getting faster. The acceleration and velocity are pointed in the same direction. If something is slowing down, then its acceleration and velocity are pointed in opposite directions. Yes?
When it's speeding up going down, doesn't that mean the acceleration is increasing?
No. In the case of gravity, the acceleration always stays the same. Gravity accelerates all objects at the same rate, and we'll find out in why in chapter 13. Okay? The acceleration of you throw a mouse or a elephant off of the building, which one hits the ground first? They're supposed to hit at the same time. Now, with air resistance, we'll get to that later. Okay? Right? But Galileo discovered that gravity accelerates all objects at the same rate. Not everything has the same force of gravity acting. Okay, we're getting ahead of ourselves. Okay? Let's get out of the weeds and come back to what we're trying to do here, okay? Which is taking this one step further, because these deltas, they represent a period of time, don't they? Okay? So what's the difference between average and instantaneous? Okay? This is a graph, a plot of position versus time. There's several of these in the book. Go back, go read how to read a position versus time graph. But if a position is changing in time, that would be represented by a line like this, okay? And what's a change in position divided by a change in time? A velocity. So this line here represents a velocity, right? So this is a trip to Los Angeles, right? You get on the 41, what's the speed limit on the 41? Okay, this is a problem, okay? It's 65.
We're not on the 99 yet.
Right, okay. So from the 41, then you get on the 99. What's the speed limit on the 99? About 7,000 miles an hour, right? Because if you're not going 7,000 miles an hour at the Jensen interchange, you're dead. Because the trucks are all going to run you over, right? Okay. Why is this steeper for the 99? We are changing our position more in a shorter amount of time, right? Now, those of you that have calculus class, okay, you know what the slope of that line is. What is it? It's the velocity. And we use a, fill in the blank. A derivative. There it is. Why is the 405 a straight line? What's the velocity on the 405? Any of you that have ever been to LA know that the 405 is LA County's designation for its largest parking lot. Right? Because you get on the 405 and what is your speed? 0. Like you're not going anywhere. People that get on the 405 pack survival gear because you're going to be there for a while. Right? So what's the velocity for a perfectly horizontal line like that? It's 0, isn't it? Okay. All right, but now the specter of the derivative has reared its ugly head. All right. Okay. I was going to ask what a derivative is. I don't want to know. But to scare you, in the limit, oh my gosh, as delta t and x and everything else goes to 0, of this delta x over delta t, we say, okay, what are we doing there? What are we trying to say that we're doing there? So it's like is my speed on the 41 the same as my speed on the 99? No, right? But I can get an average speed for this trip. Let's say that it's a 200-mile trip and it took me 4 hours. What was my average speed for the trip? 50. How'd you do that? 200 miles divided by 4 hours, right? Miles per hour is a velocity because it's a distance and a time. It's just not the perfect unit system, but it's the one we use. Okay, fine. 200 divided by 4 is 50. So that's 200. That's 50 miles an hour. Were we going 50 miles an hour the whole time? No. Okay, because On the 5, you get to the Grapevine and you discover how many people in the valley don't know how to drive in the mountains, right? And so on and so forth. And my kids get sick and I got to pull the car over and hose the whole thing out. Like just, right? Your speed isn't the same all the time. But what if I want to find my speed, say, between Gorman and Bakersfield? Which I always hope is like as short as possible because it's Gorman. Anybody here from Gorman? Okay, good. Right? There's just nothing out there, right? If I shrink that time interval, I get a more and more precise reading on what my velocity is. And if I can shrink it down to the instant I'm measuring it, like right now, what is my velocity? Then I've got what's called an instantaneous measure. In math speak, we change the deltas, the capital triangle deltas, to what? Little d's. So a change in position, an instantaneous change in position, an instantaneous measure of position, instead of being a delta x, would be a dx. And a instantaneous measurement of a change in time would be written as what? dt. This is not a derivative. I mean, okay, yes, it is a derivative. But it's not. Like, all derivatives are what? Ratios. It's a ratio. Okay? That's what they are. There's no magic. I mean, I know you've been in class and then take a derivative of x greater than 2. That's monkey work. Okay? Wolfram Alpha can do that. Right? The power behind this concept of derivative is that we're changing things. We're changing something compared to something else. In the case of a velocity, it's a change in position over change in time. What would my acceleration be? Change in velocity over change in time. Now, can I take the derivative of a velocity function with respect to t and get its acceleration function? Yes! But that doesn't change the fact that it's a change. It's a ratio. We often use a bar. Well, sometimes we don't do anything. And you can see here that I made the mistake. I did it over the A just by reflex, okay? That bar is used to indicate that we're talking about an average. We're using a delta. Sometimes it's dropped. Sometimes it's implied, where you'll see in the calculation that a delta is involved. And if you see the delta, then you know you're dealing with averages. You're dealing with over a period of time. But when we reserve the little d's, and we reserve the symbol V and A with no bar over the top, to say, no, this is the acceleration right now.
What would a change in acceleration measure?
It's called a jerk. And it's in units of jerks.
Like shaking or what?
It's kind of a measure of how fast the acceleration is changing. So it can be used like in vibration sometimes and stuff. Yeah, but it's called a jerk. Change in acceleration. We don't do that in here. Okay. I ran out of time for that quiz. In the last, when did we get out of here? 9:15, right? 9:20? I don't know what it is. Okay? You're stuck for the rest of the day. No. Let me plant an idea in your brain that we are going to use on Monday. I spent a lot of time talking today because I just assumed you hadn't read the book or something, right? So on Monday, what we're going to do is we're going to get into the nitty-gritties of working with acceleration, velocity, and time. We're going to pull some equations out. We're going to start problem solving, okay? This method that I'm going to teach you right now and continue on Monday is the key thing that you are supposed to be learning in Physics 4A, okay? I know that there's kinematics and energy and forces and gravity and all these concepts, but really what we need you to learn is problem solving, a systematic approach to figuring out anything. And by anything, I mean anything. I use this problem-solving method when I do my taxes, okay? This problem-solving method, I personally have boiled down to 4 steps. These steps mostly go in order, but there's quite a bit of wiggle in terms of going back and forth and around again. It's supposed to be a circle. It's supposed to be like an iterative thing that you do. Okay? But what I want you to take home right now is the idea of, this analogy. Let's say that you're told that you need to build a house. Okay? What are the things that you need in order to build a house correctly? What? Like gear, tools, that kind of stuff? Materials? Okay? So knowing how to do it, all right? So we've got materials, we've got knowledge. You can have all the nails and wood and concrete in the world and knowing how to do it, but you're not going to be able to do anything with it if you don't have a plan, because it's going to look, insurance, it's going to look really wonky without that plan, right? But there's another key thing that's missing. What are the things you use to make the measurement? What's a screwdriver? What's a hammer? It's a tool. You need materials. You need a plan. You need tools. Right? In order to build a house. Okay? Problem solving. What we are trying to get you to do. The problem solving method is often where you're going to formulate the plans. The materials in this class are going to be given to you in the form of word problems. Yes, word problems. This is your worst nightmare come true. Okay? The tools will be the equations, the physics, the stuff that comes. Do you approach a hammer and ask it how to build a house? Hammer doesn't know. In the same way, the equations don't know. Never start with equations if you can help it. Sometimes it's your only starting point, but most of the time, you are going to want to go straight to Mr. I always tell, Mr. Bailey, just tell me which equation to use. You're saying, don't make me do physics, right? Just let me do algebra. Okay? The whole point of this class is to know how to use the tools. So when you're going through and reading, so you're going to do chapter 1, you got to do your chapter 1 homework, right? Okay, it's due this Saturday. So Friday's a great day to come in and get help on that. And then chapter 2 reading, you need to start over the weekend because on Monday we're going to really dig into chapter 2, right? Okay, so as you're going through, you're not going to understand everything, but you're going to see equations and you're going to be like little yellow ones or outlined ones. Like, this is the key equation. I'm going to write that one down. No idea. Those are just tools. They're hammers. They're screwdrivers. They're socket wrenches. They are not the house. They are not the plan. They are not the materials, right? Keep that in mind, right? Because so many students make the mistake of thinking it's just the equations that I need. They're a piece of the puzzle. I will see you tomorrow in whatever lab you are in or trying to get into. Please make sure not to miss tomorrow. If you can't, if there's something going on, email me.